let's do a quick review of the plane stress situation and also the thermal. So for the plane stress, basically we need to expand the 1D situation to 2D space. So we have the coordinate transformation. So this is from the local coordinate, local x coordinate to the global coordinate. And so we have the final derivation is here. This is the K matrix for 2D plane truss. And of course, we will provide this one in your exam. You don't need to memorize anything. But the thing you need to be careful is that our derivation of this K matrix is based on the assumption that our angle phi here is from global to local counterclockwise. I mean, this is or our derivation in class and in the textbook is based on assumption that this angle is from global x coordinate, which normally we define this way, to local x coordinate, which if we define this one at first node, this one at second node, this becomes the local x direction, and it's counterclockwise. I don't know what B means. It's counterclockwise from global x to local x. That's the key thing. If you want to use a derived equation in our class, if you want to use this K matrix. But of course, if you insist to use clockwise their definition of the angle phi, you need to derive your own set of equation and use in your exam and in your homework. That's fine too. I'm not forcing you like you have to follow my way or the way of textbook derived equation, but just be careful about the phi. That is a common mistake in the exams. Because I mean, the equation, you just plug in the numbers, right? And this is and also for the element force, of course, this is the elongation of the bar. No matter it's in it's 1D situation, 2D situation, this is the elongation, the local x direction. And element force, because we solve for the displacement in the global coordinates, so this is how by using the global displacement in the x to y direction, displacement in x direction, we find the element force. And of course, if you know the element force, which is the same thing as what we talk about the internal force in mechanics, you get the stress, right? So when the stress is uniform distributed over the cross-section, you can simply write as element force divided cross-section area equal to sigma. This is only an assumption that stress is uniform distributed over the cross-section, which is true for tension compression. But if we get more complicated situation, let's say stress is linear change or quadratic change, like bending, you have normal stress, it's linear change. Shear, the shear stress caused by transverse shear force is quadratic change if it's rectangular cross-section. Then you cannot simply say that P of A equal to stress. It's not always like that. In that situation, what we need to do that integration of sigma over the cross-section equal to the force. And then how the stress change over the cross-section, it will change. So what we normally see like in senior design class is that in the final presentation, like they're about to graduate. And in the final presentation, they always have, no matter what stress it is, it's always force over area. It's not correct. This is like starting point of mechanics materials, but you guys are more, learn more advanced content than that. So this is only for tension compression. When stress is uniform distributed over the cross-section, we can use this one. But anything higher than this, no. It's integration of stress over the cross-section area equal to the corresponding internal force. It can be the moment, it can be the shear force, internal shear force. And of course, element force or internal force have the same sign of the stress. Tension, compression, positive, negative, that sign convention always for stress and internal force. And for this example problem, we have the K for each element. We do the assembly and we solve the unknown because node 1 and node 2, they are boundary condition, and in the end it becomes 2 by 2. And we solve the element force and reaction force. So for this one, the key thing here is that, again, commonly made mistake in the previous exam, in previous semester, is that, like, okay, students will say, It is 40, positive 45, negative 45, or it's a negative 135 or positive 45, right? This is like students always get confused. So here, let's make it clear. It's true that it can be, so I can define the positive x direction in this direction. I can also define the positive direction in this direction. I define from node 3 to node 1. Either are correct. I mean, you and your friend can define the local x direction any way you guys prefer. And in the end, you guys should have the same results as long as your process is correct. Because we need to know that, let's say I have a 1D bar in the 2D truss situation. This is the one element I take out. And you apply force, you apply boundary condition. And I want you to calculate, okay, this one fail or not? Is safe or fail? It doesn't really depend on I define this one at first node, this one second node, or this one's first node, this one's second node. All the coordinates is in the local x direction, or the node order is only for convenience of your calculation. But for this bar, if it fail or not, as long as it's same cross section, same material, same force apply, same boundary condition. If you fail, you fail, no matter how I define node, right? No matter how I define coordinate system. So it is fine. It does not. It's not like it has to be in this way. Actually, let's expand this trace a little bit, just in case anyone get confused. So I guess what he defined node order was, let's put it this way. So let's say node I, the first node, node J, the second node. So U1, U3. So the first node is node 1. The second node is node 3. So if we do in this way, we know that the local x is in this direction. That's why he said, okay, this phi should be negative 45. It's not positive 45 or not 135 or anything. So this is for the first element. And the second element, so he used from node 2 to node 3. So now let's put the angle here, phi. If I define from 1 to 3, then it should be negative 45 degree. And if I define from 2 to 3, the first node is node 2, the second node is node 3, then this is the local x direction. Now this angle becomes negative 135 degree, right? And we have the corresponding L and M cosine sine value and put into matrix, do the assembly. But it is also correct. Let's say if your friend do it in this way, node I, node J, I use 3 to 1. I use 3 to 2. It's also correct. But now you need to know that now the phi angle will be different. If I define the first node for the first element is node 3 to node 1. Now the local x direction is in this direction. This is the local x. Now this is the global x. Now this becomes the phi angle. Make sense or not? And the same thing, if I define from 2 to 3, sorry, 3 to 2. Now this becomes the local x for the second element. And again, this is the global x. Now this is the phi angle, right? So now you can see that. Okay, now let's put the angle here. So for the first element, I think the definition is from the global x to the local x. So the first one, it should be 135. And the second one should be 45 degree. And now, of course, you have different phi. You have different L and M. But in the end, as long as your process is correct, you and your friend solving from these two starting point, you should have the same answer. Because now you have different L and M, but when you do assembly, when you write the K matrix for the first element, now it becomes, if I do it in this way, it becomes U3, U1. And also the second K matrix, it will become U3, V3, U2, V2. And you do assembly, you apply boundary condition, and you solve for this. You can practice after class to see, like, if I define in this way or I define in this way, does it generate the same answer? It should, because we need to understand that to determine a structure fail or not, it should not depend on how I define which node is first node, which node is second node, right? But you just make it consistent in your own solution. Like, if at the beginning I define from node 1 to node 3, so we know that this is the local x direction, and we know what is corresponding phi angle, what is L and M. And when we write the K matrix, what is the index for the relevant column for the K matrix, and how we do the assembly. So this is the part that we need to be careful. And since this is still the beginning of the FEA, I strongly suggest, it's not required, but I strongly suggest that for you guys to avoid the mistakes, it's better to write this connective table. So you give very clear definition. What is the first node? What is the second node? So based on this first node and second node, what is phi and what's corresponding L and M? And then you do a calculation. So our TA can easily know that your mistake is really just wrong misunderstanding or just some like error, some calculation error. Because calculation error, we really try to minimize the penalty. It's only like 1 or 2 points off. But if it's really missed and it's the understanding mistake, there should be some major penalty there. So I would suggest that in your solution, really try to make it clear what is the first node, what is second node. I'm sure Dr. King explained like what is the first node and second node he used, but he didn't write it down. So just want to emphasize here, try to make it clear. I saw that the method superposition and the 3D, he only put the theory part, but without example problem. So my rule is that if there's only theory part, but there's no example problem, help you understand, it will not be tested in the exam. So this is just like for you, try to get familiar with something in a broad way of our FEA. Like we can also solve in the same way for the 3D truss. But since there's no example during the class, I will not test in the exam. But of course, this information is very important. It will be content in the exam. So now the thermal is basically, now what if there's a temperature change? We know that if apply a force, it will generate strain. And another thing that if there's a temperature change, it will also generate strain. Of course, for most of the natural materials, if temperature increases, there's extension. And if the temperature decreases, there should be some contraction for most of the materials. So now our strain, total strain becomes the strain by whatever force you applied and the strain by temperature change, right? So now for this is how we calculate element force. Derivation is very clear here. And this is for the 1D situation. This is example for 1D situation, I guess. Yes. And for the 2D, I from the note, I only see a final equation. Let's try to explain this a little bit more and add an example problem for this 2D situation, because I mean it's easy to write it here, but it's not easy for you guys to understand in this way. Let's try to expand this part a little bit.